So welcome everyone to this second day of the webinar on self-healing functionalities. This is an educational webinar where we got yesterday some very interesting presentation with the basis on self-healing, and also some specific presentations on self-healing functionalities on lithium metal given by Hidden Project, and second presentation on modeling given by Forever Project. So I thank Robert, Maria, and Rita for yesterday's presentation, very high level. You will find them uploaded, I guess, at the end of today or in these days on battery2030 website for those who want to see them again, or to see if they cannot join live during this webinar today and yesterday. So today we have a very good opportunity to have one, again, educational and interesting presentation given by Anja Marino. It will be introduced in a while from Nesling on supermolecular self-healing polymers. So then the two presentations on polymers will follow, given from our young scientist community that is growing. And I hope that all young people here that are interested to join this community can reach those people that are the ones who wrote the Manifesto of Young Scientists. And after a break, we will concentrate more on characterization, again with two lectures given by our young scientists. Do not be shy. So after each presentation, there will be a Q&A section. So use Q&A session to ask for your question, and then there will be, I'm sure that the presenters will be happy and glad to answer. So I give the floor to Nesling. Yuka, thank you for being here, and please, the floor is yours.
Thank you very much, Silvia. Hello, everyone. Today, Anja will present about self-healing electrolyte. Anja Marino is from Martin Luther University. In But Forever project, we are together trying to develop self-healing materials for lithium batteries. Anja with Professor Wolfgang Binder, they are trying to develop polymers as electrolyte and actually as separator for us. And now Anja will present supramolecular self-healing polymers, and I think we can start, Anja.
So hello everybody, hello Neslihan, thank you for the nice introduction. I will just shortly share my slides. So I hope it's working. As you can see.
Yes.
Hello everybody. I'm, as Neslihan said, I'm a polymer scientist, and today I would like to talk about self-healing polymers for lithium-ion batteries, especially focused on the material development in the scope of the But Forever project, which we are working on. So as you already know, lithium-ion rechargeable batteries consist of two electrodes, the cathode and the anode, immersed in an electrolyte and separated by a polymer membrane or a separator in order to electrically isolate the electrodes from each other. Single lithium ions are transferred back and forth between the anode and the cathode through the electrolyte during charging and discharging. Currently, mostly intercalation reactions are applied in commercial lithium-ion batteries for the storage of lithium ions, both in anodes and in cathodes, whereas normally liquid organic solvents like carbonates are used as electrolytes. The main drawbacks of the traditional lithium-ion batteries are the leachability of these volatile and flammable organic liquid electrolytes. Then we have a lithium dendrite formation, which can lead to the shortcut and the thermal runaway of the battery, as well as the large volume changes on the electrodes due to the continuous lithiation and delithiation processes in a battery. That means that the electrolytes for the next generation lithium-ion batteries need to fulfill various requirements, like prevent leakage, be less harmful, be not flammable, and ideally electrolytes should suppress the lithium dendrite formation and be able also to compensate the volume changes of the electrode. Additionally, it would be nice if they could also be easily processable. Polymers in general are crucial components of enhanced performance lithium-ion batteries and can be found either as binders for electrodes or as separators in the cell, but also as part of the electrolytes or also packaging coatings of the battery. However, different chemical reactions as well as the thermal changes during the battery operation inevitably lead to the structural changes which may cause the damage and degradation of the polymers applied as electrolytes, separators, or binders on electrodes. And this limits, of course, the lifetime of the battery. Polymers may break under the complex deformation during cycling, causing in turn a contact between the electrodes and subsequent battery failure connected to severe safety issues. So in the scientific community, significant efforts have been devoted to increase the working lifetime of lithium batteries by improving their capability of sustaining internal and external stresses, for example, cutting, breakage, volume expansion, gas release, or heat. There are different approaches to design the electrolytes for next generation batteries, reaching from less harmful and non-flammable liquid electrolytes over inorganic electrolytes to polymer-based electrolytes, either as a solid electrolyte or in a gel form. In general, it can be stated that the polymer electrolytes are significantly increasing the mechanical integrity and the thermal stability of the electrolytes, however, on the cost of the ion conductivity. So they are having in general less ion conductivity compared to the conventional liquid electrolytes used nowadays in the batteries. In the scope of the But Forever project, we are trying to introduce self-healing polymeric materials in different parts of the lithium-ion batteries. Self-healing polymers in general are polymers which are able to spontaneously repair themselves after damage. And we are working on one side on the self-healing polymers, which can be used as the binders for electrodes, which are able to compensate the volume changes of the electrode during charging and discharging, and thus preventing the cracking and pulverization of the electrode with time. On the other side, we are working on the design of the novel self-healing polymer electrolytes, which are able to autonomously repair the micro cracks during the battery cycling, while simultaneously suppressing the lithium dendrite formation and stabilizing the electrolyte interface in the battery. In general, self-healing processes in polymer materials can occur either with or without external stimulus, so-called autonomous, and can generally be classified in two major groups as extrinsic self-healing, where the self-healing agent is embedded in a capsule or in a vascular system, or as intrinsic self-healing, where we use a reversible reformation of chemical bonds within the material. Within the But Forever projects, we focus on intrinsic self-healing by introducing reversible bonds into polymeric materials. Internistic self-healing is an autonomous self-healing process, so we don't need an external stimuli, and it depends on the tailoring of the dynamic bonding interaction at the molecular level, or framing an interplay between the diffusion and entanglement of polymer chains. In general, there are two possibilities to introduce self-healing functionality into polymeric materials, either via so-called supramolecular interactions or via dynamic covalent bonds. Supramolecular chemistry is based on reversible non-covalent bonds, which primarily break upon mechanical damage or stressing, leaving behind a kind of sticky functionalities which are preserved on the freshly formed interface after the cutting. That means these sticky parts are actually multiple unbonded supramolecular bonds, which then can rearrange, recombine, and restructure in order to heal the material. The most important factors which are influencing the supramolecular interaction and subsequently the self-healing are the strength of the interactions. That means that depending on the kind and the number of the interaction, we can have either a stronger or weaker supramolecular network. And of course, also the dynamic of the self-healing process is important. That means how fast these non-covalent bonds are rearranging and opening and closing it again after the damage. In general, we can have a numerous supramolecular interaction, which include hydrogen bonds, metal ligand coordination, electrostatic or ionic interactions, host-guest interactions, PP stacking, dipole-dipole interactions, and also van der Waals interactions. On the other side, we have the possibility to introduce the whole so-called dynamic covalent bonds. That means that this dynamic of the opening and closing of the covalent bond can be generally achieved by shifting the equilibrium from an energetically higher to the energetically lower state. The basic principle of the self-healing via this dynamic covalent bonds is the opening and closing of the bonding side, which leads at the end to the corresponding equilibrium. The control of this equilibrium, which is here schematically presented, can be triggered by different stimuli like irradiation, pH value, moisture, catalytic activity, and temperature. Temperature or heat is the most used trigger because it's easily tunable and of course relevant for different applications. Then we also have the possibility to use different kinds of dynamic covalent bonds for the self-healing materials, including Diels-Alder reactions, disulfide, diselenide, or siloxane exchange reaction, boric ester bonds, imine bonds, transesterification reactions, but also alkoxyamine bonds, for example. In the scope of the But Forever project, we strongly focus on so-called ionic liquids and ionic liquids-based materials. Ionic liquids are more or less organic salts, which contain bulky organic cations and different type of anions. They are salts and contain solely from ions, and in most of the cases they are even liquid at room temperature. They have some unique properties like negligible vapor pressure. They are thermally stable and non-flammable. Additionally, they exhibit high ion conductivity and a large electrochemical window, which makes them suitable for different kind of electrochemical applications. Even in the liquid form, ionic liquids can be used as a promising alternative for the flammable organic electrolytes in lithium-ion batteries. But in order to introduce the self-healing functionality into this kind of materials, we may have to make them more solid. There are in principle two ways to combine ionic liquids with polymeric materials. Firstly, we can just physically embed the ionic liquid into polymeric matrix. And these are so-called ion gels, or we can use an ionic liquid as a monomer itself and then produce the so-called polymeric ionic liquids. The role of the ionic group is, of course, to enhance the ionic conductivity of the materials, whereas the polymer fraction should give the distinct mechanical stability to the desired material. In order to achieve the self-healing functionality, we can also add additional self-healing groups, either supramolecular groups, for example, like here, the quadruple hydrogen bonding UP group, or we can go to the dynamical covalent bonding and introduce, for example, boric ester linkage into the polymeric material to achieve the desired self-healing. When we talk about the development of self-healing binders for electrodes in the scope of the But Forever project, we focused on the silicon anode, and on the other side on the core shell NMC cathode material. Due to its high specific capacity and the high natural abundance, is silicon a promising alternative to the conventionally used graphite anodes. However, the main drawback of the silicon anodes is the extreme volume changes during charging and discharging, where we can observe the volume expansion up to the 300%. And what happens then, firstly, this repeated volumetric changes due to the expansion and the shrinkage of the silicon particles can lead to the loss of the particle-particle contact, followed by the electrical isolation of the silicon particles and the elimination of the composite electrodes and current collectors. Secondly, the parts of the organic electrolytes form a thick and unstable SEI layer, so solid electrode interface between the electrode and the electrolyte. And when we have these repeated volume changes, this also leads to the breaking of the SEI layer, and then the SEI layer has to be repeatedly freshly built up. That leads to a continuous usage of lithium ions and the electrolytes, and of course shortens the lifetime of the battery. On the side of the NMC cathode, we don't have this enormous volume expansion. We have volume changes of 7 to 10%. However, it is observed that we during the charging, discharging, distinct manganese loss can be observed when the NMCs are used as the cathodes. When we look at the previous research and the literature regarding the self-healing binders for electrodes, everything has started with the pioneering work of Bao and co-workers in 2013, and this inspired the worldwide research of self-healing binders for silicon anodes. They used reversible hydrogen bonding of urea groups to create a self-healing polymer binder, which was in contrast to the classically used binders, was able to compensate the internal mechanical stress caused by the volume changes of the silicon microparticles while still remaining conductive and autonomously repair the micro cracks which were appearing during the cycling of the battery, and hence significantly increase the lifetime of the silicon anode. Another interesting example is presented here on the right. You can see a self-healing binder where the quadrupole hydrogen bonding supramolecular UP groups are used in order to introduce the self-healing function. Here, a very small amount of the UP groups have been incorporated into the linear chains of polyacrylic acid PAA. Polyacrylic acid has been widely investigated as a binder for silicon electrodes also on its own due to the presence of the large number of carboxylic acid groups which are capable to undergo hydrogen bonding among each other and with the silicon anodes. And this provides a good chemical stability of the electrode during the cycling. The incorporation of the UP groups results in the formation of this kind of supramolecular polymer network around the particles, which offers a strong adhesion strength with a silicon nanoparticle, and was able to withstand large volume expansion and the release of the internal stress of the particles during the lithiation and dilithiation processes. Let us now look more closely to the design of self-healing polymer electrolytes. As we said, we have the ability to embed the liquid component like ionic liquid physically into the polymer matrix and gain the gel electrolytes. Here, the polymer component is increasing the mechanical stability unto the distinct extent, whereas the liquid component is staying more or less mobile and is able to increase the ion conductivity of the electrolyte. In the solid electrolytes, we have increased mechanical stability, but on the cost of the ion conductivity. However, the polymer electrolytes can be damaged, and the introduction of the self-healing functionality can increase the lifetime of the battery. Here is one example of the solid polymer electrolyte. We have a copolymer where we have a polyethylene glycol groups to increase the lithium ion conductivity. We have the UP groups for the supramolecular network, but then also a dual network is formed via chemical cross-linking of the polymers, which significantly increase the mechanical stability of the polymer. However, only 10 to the power of minus 5 Siemens per centimeter ion conductivity could be reached. Another interesting example with the UP group is presented here. This is a self-healing and also shape memory solid polymer electrolyte, where we have again the polyethylene glycol side chain, and the UP groups, but here we have polyvinyl alcohol as the basic polymer. The polyvinyl alcohol features numerous properties which makes them promising candidates as a polymer matrix for solid polymer electrolytes. They have good thermal and mechanical properties. They are non-toxic, exhibit a relatively high dielectric constant, and a good film forming property. After cutting, as you can see here, this film can successfully be self-healed after 2 hours at 60 degrees. And if then at 60 degrees, we can change the form of the polymer film, for example, by rolling. And then when it's freeze under in the liquid nitrogen, we can obtain a spiral-like shape. And then when heating it again, this temporary shape is lost again, and we have our initial shape of the film. This is can be achieved due to the temporary shape, can be achieved due to the interaction of the PVA with the polyethylene glycol side chains, whereas the supramolecular network is giving the possibility for the permanent shape of the film and the mechanical integrity. Another interesting example of the same working group, in order to increase the thermal stability and fire resistance of solid polymer electrolytes, they added cyclophosphates-based compounds into this polyethylene glycol UP polymer, and due to the presence of the conjugated rings rich on nitrogen and phosphorus, the obtained solid electrolyte had pretty excellent flame retardant properties, but also the present UP groups and hydrogen bonding enabled the supramolecular networks, which could be healed within 3 hours at 60 degrees. But we also don't need only to use one kind of self-healing functionalities within the polymer matrix. We can also combine several of them, for example, like in this case, where we have a combination between hydrogen bonding networks combined with disulfide dynamic covalent bonds, which then together gives a more mechanical integrity to the polymer matrix. And this optimized electrolyte could heal at 30 minutes at room temperature without any kind of external stimuli. As I said, in BAT Forever project, we are combining the ionic liquid with the polymer materials. On one hand, we are using ionic liquids as the monomers, preparing the polymeric ionic liquids, which can either be cationic, anionic, or zwitterionic polymers, or we can just embed the ionic liquid into polymer matrix, preparing the ion gels. Ionic interaction itself are also a kind of supramolecular interaction and could provide a self-healing. However, in the ionic liquid, the ion clustering is not strong enough to provide efficient self-healing, and that's why we have to add an additional self-healing functionality like hydrogen bond or some other dynamic covalent bonds into the polymer matrix. Here are some actual results from the project. So here we have the possibility to prepare the copolymers, which contain on one hand the ionic liquid groups, and on the other hand the UP hydrogen bonding units for achieving the self-healing. So-called so prepared polymer material can be self-healed within 1 hour at 40 degrees, and the tensile testing have shown that the mechanical integrity of the materials was re-established after 1 hour at 40 degrees. If we then add lithium TFSI salt, for example, we can increase the ion conductivity of the material, which makes it suitable for the application as electrolyte in lithium-ion batteries. Beside hydrogen bonding, we can also use dynamic covalent bonds like boric acid ester bonds, which can be combined with ionic liquid-based polymers, resulting in self-healable and reprocessable materials. For example, after cutting, the material can be self-healed at 80 degrees in 30 minutes, and approximately 65% of the original state could be restored within 1 hour. In order to investigate the reprocessing ability of the material, we can cut it in small pieces, and after hot vacuum pressed at 40 degrees and for 4 hours, we can, as you see, obtain the film with the preserved integrity of the sample. And finally, one of the more additionally interesting features of this kind of materials and is that they are also 3D printable via fused deposition modeling. That means that we can have a opportunity to much easier introduce the electrode into the battery cells, and also this enables us to design different battery architectures. And thank you for your attention, and I'm open for your questions.
Anya, this was a very great presentation. Thank you very much. And do you have any questions, guys? Actually, I have 2 questions here. Both of them are coming from Envy Group, Anya.
Yeah.
I can read the first one if you want.
Yes, please.
Emre is asking that how to calculate self-healing kinetics, and does it have an impact on designing supramolecular materials?
So it has, of course, it has the kinetics or the dynamics of the self-healing has an impact on the design of self-healing materials. There have been, however, it is actually the calculations. For the calculations, a lot of basics research is needed in order to really calculate the exact strength and the dynamic of the reversible bonds in the self-healing materials. And of course, if you have, for example, as in our cases, if you have a combination of 2, like hydrogen bondings and ionic liquid or ionic interactions in between, then of course a lot of basic research has to be made in order to really estimate in before synthesizing the expected strength and behavior of the bones.
Yeah. Okay. Thank you, Anya. And second question is coming from Ömer from Enver. As we all know that UPY with counter polymers such as PAA or PVA work effectively as a self-healing polymer matrix. However, the battery application of self-healing polymers is a bit complicated due to the challenge for monitoring healing process. How can you monitor the healing process?
The monitoring of the healing process, it's yeah, not that easy. We can from outside monitor the performance of the battery and see how indirectly see the prolongation of the battery lifetime with self-healing materials. Directly monitoring, we would have to have maybe a sensor materials built inside to, for example, monitor the pressure on the materials and the response of the materials on the pressure within the cell.
Yeah, actually, a few weeks ago, we had another workshop, maybe you remember, In that workshop, we also discussed about that, how we can monitor or characterize this healing process. And a good actual suggestion came from Feryat in Enver Group. He said that maybe we can use CT tomography, computational tomography, to check this healing process. And if we can use maybe in situ characterization methods, so maybe it will be easier to monitor this self-healing process.
Yeah. Yes, that's a good idea.
And another question is coming from Samson from IFE. Is there a limit to the number of times a polymer can self-heal? How many cycles are typical or have been demonstrated?
So with the reversible bonding, theoretically, it is an unending, non-ending storing, and the reversibility should be can be repeated multiple times. But if you see here, for example, graphically shown, ideally the self-healing material should be continuously be able to self-heal itself, but in the reality, of course, the self-healing efficiency is decreasing with time. But practically, in any case, numerous cycling are possible. However, that of course depends on the material and is strongly differing from one kind to another.
Yeah. And also from battery side, we would like to reach around 1,000 cycles. So we can say maybe 1,000 times we should have these reversible reactions.
Yeah.
And another question is coming from Vadeleda. Thank you for your presentation. It was a very interesting work. I have some questions regarding some of the work you have mentioned. What determines the healing temperature for different types of materials? And what are the advantages and disadvantages of healing at room temperature and at elevated temperature? Which healing condition is more applicable to real battery application in your opinion? If you want, I can read each of them.
I will try. So first, of course, ideally, the best self-healing should be at the room temperature and possibly very fast. What is limiting the efficiency is the dynamic of the opening and closing of the bonds. And it is known that at higher temperature, of course, this opening and closing processes are faster as at room temperature. That means that for different types of materials, it is in most of the cases try and error principle. So everybody is firstly trying to see the efficiency at the room temperature. But however, if the self-healing process is lasting too long for the practical application, then the moderate increase of the temperature is used. And then depending on the kind of the material, we are going to the higher temperatures. And depending on the, but of course, depending on the application, also in some cases, the higher temperature of, I don't know, 60 degrees is not limiting because we already have it in the application. So it's still usable material for this kind of applications.
Actually, I was also wondering about that. I had my note that I was planning to ask you, do you have any plan to work for room temperature materials? Because in Enver said, you know, our metal is working in room temperature. Do you also have any plan to work on room temperature self-healing polymers?
Yes, we have.
Okay, good. So another question, it is very similar to that one. Is the temperature of self-healing activation always directly correlated to this type of self-healing mechanism?
I'm sorry, I now didn't really understand the question.
Is the temperature of self-healing activation always directly correlated to the self-healing mechanism, type of the self-healing mechanism?
Not only. If you remember of this several examples, so there have been different materials which are both based, for example, on the hydrogen bonding via UP group, but they are self-healing at different temperature. Some of them at room temperature, some of them at 30, 40 degrees. Besides the kind of the bonds, also the mobility of the polymer chains plays a role. So the polymer chain backbone, if the polymer backbone can move faster or easier, then also the supramolecular bonds can easier come to each other again and heal the material. So the interplay between the self-healing groups and the polymer backbone itself at the end give this final self-healing temperature.
Okay, another question. I don't know who is asking that. In your slides, you show the use of ethylene glycol-based monomer during the synthesis of self-healing polymers. Regarding your But Forever synthesis slide, why didn't you use an ethylene glycol-based monomer as your self-healing polymer?
So yeah, yes. For the But Forever project, we prepared different kinds of polymers. In this case, this was kind of a first trial, and we wanted to incorporate only 2 different kinds of monomer to see firstly the influence of the ionic groups on the presence of the UP group and reverse. And of course, in the meantime, we also have used the monomers containing the polyethylene oxide side chains with a cooperation with ENUA. The EMRE was that were lots of discussions with EMRE to come to the and introduce also the polyethylene oxide side chains.
Yeah. And another question, Anya. Is silicon anode still a viable option compared to graphite? That's with its drawbacks like volume expansion, excluding capacity.
So in my opinion, as a polymer science, yes, but I think that you can better answer this question as our battery expert.
Actually, yes. Maybe since 8 years, we are working on this silicon anode material. The capacity is really very promising when we compare to graphite. And when we use silicon, we can assemble very thin batteries, and this provides us higher volumetric capacity. You know, for example, for electric vehicles or for drones, the weight of the battery and the volume of the battery is very important. So from starting the capacity of silicon, it provides us very advantage to use it. And because of this advantage, we are trying to solve the disadvantage of the silicon material. So still, I am thinking it is viable to work on it. Is there any other question? Last one, Badril Ashar, thanks for nice presentation. What is the correlation between the mechanical properties and self-healing performance?
I'm not sure that I really understand the
I can read if you want.
Yes,
I can
please.
read one more time, Anya.
Yeah.
What is the correlation between the mechanical properties and self-healing performance?
Yeah, it's it's a balance. So we cannot produce a very highly rigid, strong material and in the same time expect it to have a self-healing properties, while the self-healing you need at least a little bit of motion of the groups and the polymer chains. So there is kind of limits of the mechanical integrity which you can reach with the self-healing material. So you cannot have a very highly rigid material and with the self-healing properties at the same time.
Yes, if we are talking about the silicon especially, it is already a problem to have these to develop these mechanical properties of the electrodes. So if we can have good self-healing performance, so that means we can improve the mechanical properties of the silicon and at the same time the anode structures, because our aim is here to keep the integrity of anode. So this is why it is very related to each other. Still, we have a few minutes, so maybe I can ask a question, or maybe someone wants to ask a question. Oh,
yeah, if I may, I have one question.
Yes, sure.
Yeah. Thank you for this nice presentation. You have shown through the presentations that some people have shown the self-healing ability through cutting the polymer film and then seeing how fast or easily it goes back together. I would like to know your opinion on how representative this characterization is with what is happening in the actual battery. So I think it's a little bit related to understanding the self-healing mechanism in the application and how, yeah, we can correlate the two characterization methodologies.
So I think that for the lab conditions, it is pretty representative. I'm not personally not really a fan by only representing a self-healing by cutting and then sticking and then okay, it's healed. It's healed. I would always include an additional test like mechanical testing, so that really the functionality of the materials is then tested and compared like before and after cutting. So the cutting test alone with a picture of the self-healing material, I wouldn't use it as a, I'm not a fan of it.
Okay, thank you. Yeah, I just wanted to know your opinion. Thanks.
Yeah, thanks. And last question I would like to ask, you also mentioned about this SEI layer when we are using this conventional electrolyte. And the product of these electrolyte, forms as SEI on our anode. And what do you think about these self-healing supramolecular binders or polymers can affect the SEI stability?
Depending on I think that a good working self-healing polymer can increase the stability of SEI layer, because it gives a distinct elasticity, so that it wouldn't be braked at the beginning, how to say. So I think that it can have a pretty good influence on the SEI layer.
Okay, thank you very much. Is there any question? Okay, I think we are on the time. Thank you very much for this nice presentation, Anya.
Thank you. Thank you for the invitation.
Yeah, and thanks for joining us today. Yes, or who will take now? I think Tamara.
Um,
Now we will start next presentation.
yes, I think it appears that Sylvia lost her connection maybe somehow. So if we could move on with Mikkel, self-healing functionalities for polymer electrolytes.
Hello.
Hello.
Hello. Thank you for having me here. I will share my screen. I hope
Perfect.
you can all see it. Yeah. Is
Yes.
it okay?
Yes. Go ahead. Thank you.
Perfect. Well, thank you for having me here today to talk about self-healing functionalities for polymer electrolytes. Today I will cover some introduction on why we use polymer electrolytes for batteries, and then I will move into these self-healing functionalities, of which some of them have just been covered by Anya in this very nice presentation about the Bat Forever project. So currently in lithium-ion batteries, we are using. No, let's go. Yeah. We are using organic liquid electrolytes, which are highly volatile and narrow the operating temperature window of the batteries, and most importantly, they limit the negative electrode to carbon or carbon silicon materials, as we've seen in the last presentation. This limitation comes mainly since the use of lithium metal negative electrodes leads to the formation of lithium dendrites, which poses a risk for the battery, since they might lead to cell short circuit, thermal runaway, and at the end the risk of fire or explosion of the battery. And also the inability to use lithium metal electrodes leads to a lower energy density in the battery. So therefore, the use of solid state lithium metal batteries with solid electrolyte increases the safety of the battery, since these solid electrolytes are less flammable, and in addition, the ability to use lithium metal electrodes partially hinder the formation of dendrites, and therefore the batteries. So the batteries are safer and also have a higher energy density. In terms of energy density, we compare applications such as electric mobility. So an electric vehicle, Tesla electric vehicle with a lithium-ion battery, with the current energy, has a driving range of around 550 kilometers, whereas a solid-state lithium metal battery, for example, with technology developed by Solid Power, has a higher energy density, which would increase the driving range up to nearly 800 kilometers. So the main two advantages of polymer electrolytes are, on the one hand, safety, and on the other hand, increased energy density. So what is a polymer electrolyte? So as you all probably know, a polymer electrolyte is comprised by one or more lithium salts and one or more polymer matrices, and this lithium salt is solvated in the polymer matrix. So typical example is polyethylene oxide with LiTFSI, where the lithium cations are coordinated by ethylene oxide groups, and both the lithium cations and TFSI anions are mobile through the polymer matrix. So where do we have in the solid state battery, which functions does this polymer electrolyte fulfill, or where do we have the polymers located in the polymer matrix? So first we have the polymer acting as electrolyte and a separator, which fulfills two functions at the same time compared to a lithium-ion battery. It fulfills the function of being an ionic conductor, meaning the electrolyte, and fulfills the mechanical separation of both electrodes, so being the separator. And in the positive electrode, in the cathode, the polymer electrolyte also fulfills two functions. So it is the ionic conductor in the cathode, so we call it the catholyte, and it is also the binder of the active material particles, which is also a mechanical function. There are actually three different regions that we've identified where polymer electrolyte can have self-healing functionalities with different types of functions, which would be the interface with the lithium metal negative electrode, the bulk electrolyte, and the positive electrode with the active material interfaces and the interfaces with the electronic conductor, the carbon additives. So there are a wide range of functions that a wide range of applications for which a polymer electrolyte can be functionalized with self-healing functionalities that can be solved. If we look, as we saw in the presentation by Robert Domingo yesterday, we can classify the self-healing into two different types, which is extrinsic, which is subject to external detection of the damage, so through a sensor, and this would activate, for example, an increase in temperature, leading to the release of liquid in capsules or reservoirs, or a higher amount of lithium salt. It doesn't have to be a liquid. Whereas the other type of self-healing would be intrinsic self-healing, which is the reversible formation of weak chemical bonds or supramolecular interactions. And here the process is designed through the functionalization of host material with specific groups. As Anja just mentioned, this can lead theoretically to a perpetual mending cycle of the material, and this is the type of self-healing which we will be focusing now. So within intrinsic self-healing, we have non-covalent and covalent bonds, which I gather here different examples of self-healing through these two type of bonding. So for non-covalent bonds, self-healing includes a wide variety of chemical interactions that can generally be grouped under supramolecular dynamic chemistry, and it requires a lower energy to be activated, this self-healing, compared to this covalent bond. So for non-covalent bonds, it is around 10 kilocalories per mole, whereas covalent bonds require a higher energy, and this leads to also the healing of through covalent bonds leads to a higher mechanical stability. So moving into the different examples for non-covalent bonds, we have first example is hydrogen bonds, which, as you all probably know, it's formed by a hydrogen atom and the lone pair of an electron-rich donor element such as nitrogen or fluor, and this is widely employed in the literature, particularly this uridopyrimidinone, since it forms a quadruple hydrogen bonds, and it can be easily co-polymerized with other polymer matrices through this amino group groups. So in this example, for example, the UPY is copolymerized with NCO and PVA to form a network where different UPY groups. So here there are four quadruple hydrogen bonds, as we see in the previous presentation, that self-repair. So if the polymer electrolyte, as we can see in this figure, if it suffers a cut due to the formation of a dendrite, for example, or a mechanical strain, the hydrogen bonds would allow to repair this rupture. And several examples in the literature show how the membranes self-repair after performing a cut, generally through the application of heat. This is just a lab example, as we saw in the previous presentation. If we move to the electrochemical performance, this self-healing allows to increase the cycle life of the battery with these polymer electrolytes. So here on the left-hand side figure, we can see lithium stripping and plating with self-healing functionalized electrolytes, or in blue, and non-self-healing electrolytes in gray. So the lithium stripping and plating over potential is much lower in the self-healing functionalized material. But it is of particular interest the scanning electron microscopy images, which confirm how homogeneous interfaces can be achieved by incorporating these self-healing functionalities. Since on the top row we can see the lithium metal surface with non-functionalized self-healing material, and on the bottom row we can see how it is much more homogeneous, the lithium surface after lithium stripping and plating process. Another type of this non-covalent bond self-healing would be the ion dipole interactions, which may also provide self-healing functionalities. In this example, this positively charged ethyl methyl imidazole forms an electrostatic attraction with a polymerized hexafluorobutyl group. And although this is a weak interaction, it is enough to heal this broken electoral membrane, offering good mechanical properties after the healing. In terms of electrochemistry, membrane containing self-healing functionalities, as in the previous case, offers a much lower lithium stripping and plating over potential. And going again back to the scanning electron microscopy images, the non-healing, no self-healing, the electrolyte with no self-healing functionalities has much more lithium agglomerates on the surface that can lead to potential dendrite formation, whereas the self-healing functionalized polymer electrolyte leads to a smaller amount of lithium agglomerates or dead lithium formation, which can lead to nucleation sites for potential dendrites. And the third example would be this pi-pi stacking, which might offer self-healing functionalities through the non-covalent interaction of pi bonds in aromatic rings. This occurs generally through a pi-teeing, so these T-shaped interactions, or through stagger stacking, which is this parallelly displaced stacking of aromatic rings, and occasionally via direct stacking, so this sandwich structure we call it. So to the best of our knowledge, polymer electrolytes with metal electrodes usually don't comprise this type of self-healing technique due to the reaction of the aromatic rings and the metal electrodes. However, there is an interesting approach in the literature that uses pi-pi stacking in the lithium salt anion. So this allows to increase the lithium transference number and increases the lithium stripping and plating lifetime of the battery compared to, for example, an LiTFSI lithium salt, and also increases the cell lifetime in full cell with a lithium iron phosphate positive electrode. In terms of covalent bonds, self-healing via these covalent bonds may offer improved mechanical strength to the kill material. However, the reversibility of this bond is shorter, and an external stimuli, such as application of temperature, is generally required to induce this recovery. Therefore, the energy required is higher than for non-covalent bonds. There are different examples. So first, looking at the exchange reaction with these sulfide bonds, here in this exchange reaction, the self-healing moieties continuously exchange within the network, and this reversibility is due to the low energy required for these bonds compared to other covalent bonds bonding self-healing techniques. The energy required is still 6 times higher than that for not covalent bonds, which we approximately said it is 10 kilocalories per mole. Therefore, this is considered kind of an intermediate step between the energy required for non-covalent bonding and for high energy demanding or consuming covalent bonds for self. In this example, these sulfide bonds are exchanged to reheal the polymer electrolyte membrane, and the use of these disulfide bonds allows to increase the battery life, as you can see in this figure, compared to only hydrogen bonding containing membranes. Self-healing via these disulfide bonds occurs at temperatures higher than the glass transition temperature of the polymer, Therefore, it is ideal for polymer electrolytes, which usually operate under these conditions at temperatures above its glass transition temperature. And finally, the last example would be the addition reaction, which is particularly suitable also for polymer electrolytes since it functions well with hydrophobic polymeric materials. It is sufficiently reversible through the application of temperature for its activation, and self-healing is induced through a partial depolymerization, which occurs at the fracture site and reforms the moieties needed for the healing. The most representative example is the Diels-Alder click reaction, as we can observe in the example. A conjugated DN and a substituted electron attractor alkene react to form a substituted cyclohexane, which functions as bridge between two polymer matrices. This one is easy to break under rupture, but can easily recover and heal after increasing the temperature to 60 or 70 degrees, where a retro Diels-Alder reaction occurs, producing a number of functional groups that under cooling may react and reform the broken bonds. In the example, we observed the comparison between a battery with a non-broken and a healed electrolyte, so the red and the blue curves, where the capacity retention is quite similar. Therefore, meaning this Diels-Alder self-healing, it is quite mechanically stable and allows to nearly reach the conditions of the membrane originally had. So overall, self-healing of polymer electrolytes increase the lifetime of batteries through the repair against rupture of polymer membranes. And this healing process is stronger through covalent bond healing, such as the addition reaction. However, it requires a higher amount of energy than non-covalent bonds. Nevertheless, the electrolyte rupture is not the only degradation problem of solid-state batteries. Another mechanisms or routes are required for other common issues with polymer electrolytes, and this is still a field to be explored in the literature. So I mentioned earlier in the beginning of the presentation that there are different sections in which a polymer has a function within the battery. So if we look at the problems we might find in this battery section, we have at the positive electrode the oxidation of the polymer matrix due to the use of high voltage active material, or the corrosion of the aluminum current collector, generally produced by the anion of the lithium salt. These are two issues that are usually not addressed with self-healing techniques, but that might have its field, its space for research. In the negative electrode, the formation of lithium dendrites or the formation of dead lithium. There are some works on this, but there is still an extensive field of research. And in terms of the bulk electrolyte, the electrolyte decomposition and the lithium salt consumption, which it's generally related with the electrodes, but it's a problem of the final bulk conductivity of the electrolyte. So all these fields are places where self-healing would have its bit of research to be done, and where it can, in my opinion, improve the problems for solid-state batteries comprising polymer electrolytes. So this is my last slide. So thank you all for your attention, and I'm open for any questions in the Q&A session. Thanks.
Thank you very much, Mikkel. Sorry for not being visible before, but I got some issues with connection, but now they looks to be solved. So thank you very much. We can give the floor to Tamara, who will give us the lecture on self-healing functionalities for polymer binders. And after that, we will have a Q&A session for both of the two. So please start writing your questions in Q&A. Tamara, are you here? Can you eventually share the screen? Okay, great. Now we can see your screen.
Thank you.
We cannot see you, eventually, if possible.
Ah, can you not see me?
Okay, now we can see you. Perfect. Maybe you had just to speak. So thank you very much, Tamara. She's a PhD student in Uppsala University, so one of our young scientists. So very proud to have you also here, as Michael before, and the floor is yours. Thank you very much.
Thank you. Yes, so I'm a PhD student in Uppsala, where the Battery 2030 Plus meeting will be held. So hopefully you can come here and see the beautiful city of Uppsala. And in May, probably better weather than we have right now. So I will be talking about self-healing functionalities for polymer binders, and maybe fill in, also continue where Anja was talking about binders as well. So hopefully we'll get some more info. How I will structure today is that I will focus on silicon as an active material, because that is what I am working on. So I will show some typical binders used for silicon, go through the self-healing chemistries just briefly, since we heard a lot about that already, and then show some example about how these functionalities are used in binders for silicon anodes. So just to show you, in the lithium-ion battery, we will only focus on the active material that is silicon for the anode. So we are here. And if we compare the theoretical capacity for silicon to graphite, which is the current use of the anode, it's almost 10 times as high. But as you've seen before, there is issues with silicon. Otherwise, we would use this for the capacity already. So during lithiation, the silicon particles expand up to 300% of the original volume. And during delithiation, the material cracks, and this makes the material break down, and we are not able to utilize the capacity of it. So as a result, the capacity fades very rapidly. And we need something to repair this damage spontaneously. And here is where the binder comes into play. So if we utilize the binder and add groups that can break and form along with these volume expansions, we can make the material, hold better together and avoid these cracks. So we want to use the binder. The binder is then a polymer that sticks everything in the electrode together. But other than that, it doesn't really have any electrochemical function. So it's dead weight, and we want to use as less of it as possible. Some common binders that are often used for silicon is carboxymethyl cellulose, CMC, polyvinyl alcohol, PVA, and polyacrylic acid, PA. And I think you've seen these ones in the example shown before. So these are very popular for and works quite well with silicon. If we just look again briefly at the self-healing chemistries that we heard about, we often divide them into this intrinsic and extrinsic self-healing, as Anja also mentioned before. And these latent functionalities enabled by supramolecular interactions like hydrogen bonds or dynamic covalent bonds are coupled to this intrinsic self-healing. And this is where I will be putting my focus today, because these ones are very good for binder system, since they have multiple healing cycles and have this reversibility that we can utilize. This extrinsic self-healing, for example, is where you can use microcapsules or these vascular networks and put the healing agent inside and more locally spread the healing agent inside in the battery or where you want it, and use the self-healing through that. But my focus will be on this intrinsic. So these intrinsic self-healing chemistries can be very efficient to inhibit the volume changes during cycling, and also holds the active material together. So we improve both the mechanical and the electrical robustness of the electrodes. Hydrogen bonding, I would say, is the most preferred strategies so far for binders. But dynamic covalent bonds presents more mechanical stability. So they're also a good option to use in these self-healing binder systems. If we look at some requirements we have for our binders, is firstly that it should be water soluble, because we want an environmentally friendly and easy to handle solvent. We need good adhesion to the silicon particles for the system for the interface to be stable. And we can get this, for example, through PA gets this with the linkage between carboxylic acid and hydroxyl group to the silicon oxide layer. To cope with a mechanical stretch, we need somewhat of a stretchable polymer that is able to follow these volume expansions that we have. So it needs to be quite stretchable. It is also important that this dynamic cross-linking is quite homogeneously spread through the polymer chains to help the silicon some sort of in the same way throughout the particle, so it's even. And of course, we need a high reversibility of the bondings so that we are able to form and reform them many times throughout the cycling. So I will show some example of binders now, and first functionality is based on hydrogen bonds, and thereafter we move on to the dynamic covalent bonds. So in this example, they have used a self-healing binder based on this polyether thiourea groups here, and they use the abundance of hydrogen bonds to form these from the thiourea units. And I don't know how many Swedish speakers we have, but in this paper, they describe this binder quite as a Swedish word we call lagom, meaning that it's not too much or too less of anything. It's quite perfect for the system. So the binder is stiff, but not too stiff, and quite soft, but not too soft, and makes it very compatible with silicon. And you see here, they compare it with CMC and PVDF binders, and it shows greater capacity than both of them separately. Another example of hydrogen bonding is this, where they have used a randomly branched hydrogen bonding polymer with an amorphous structure and a quite low glass transition temperature, which the author claims makes making it easier for the polymer chains to rearrange where the fractured interfaces are. And they are very easy to form and break in the system. And they also show better cycling performance, both compared to two different binders, but also they compare it with a more stretchable polymer without the self-healing functionality, to indicate that the improved capacity comes from the impact of the self-healing groups and not the polymer just being stretchy. In this paper, they have also shown an interesting evaluation of the self-healing properties. And this one they will talk about later after the Q&A and after the break. So you will hear more about that. Here's the difference. They also use hydrogen bonding, but in a 3D network, because they claim that it makes it more mechanically stable through the volume changes. So here they have a conductive self-healing hydrogen with a 3D network based on this PDOT PSS coupled with PVA as the binder. And this network functions both as the binder and the conductive additive. And the authors mention here that conductive binders are often have a more stable electron transport compared with traditional conductive additives that we use, which tends to more easily lose contact with the silicon particles. And they also compare this with if they would use only a conductive polymer as the binder, but they say that this will not cope with the volume changes of silicon as its own, but they need this 3D network for it to function. So according to the authors here, we get the best of both worlds, both getting a more stable conductivity along with the healing of the binder. So when using this in a battery system, this provides better stretchability, electric conductivity, and increased capacity. This one is in red, the ESVCA here. If we look at a new example published in September last year, they also use a 3D multifunctional network based on also PVA, starch, and the sodium tetraborate. And this system is utilizing the OH groups in PVA for an increased adhesion to the silicon particles and dynamic covalent bonds in form of borate ester here to cross-link the polymer system. And this also provides a greater stability in cycling and an increased cycling performance compared to the two binders separately. Also in this paper, as in many of the others, the mass loading is rather low. So it's around 0.4 milligram per square centimeter. So that is something that can be improved further on. This example utilizes a host-guest interaction between this hyperbranched cyclodextrin polymer and a dendritic gallic acid and gives a supermolecular crosslinker. So the dynamic cross-linking here is referring to the reversible cross-linking with the host-guest interaction, and which can restore the broken linkages between the polymer chains during cycling. What is also worth mentioning here is that this compound can be synthesized on a ton scale through enzymatic degradation of starch, which makes it rather available. And here they mention the mechanisms of self-healing briefly, but they do not really advertise it as the main thing. It is not even in the title of this paper. And I will come back to why I think this is rather interesting later. My last example is this one, where they used elastic covalent bonds. And they have also based their binder on PAA here and focused a lot on the mechanism of the binder during the expansion of the silicon particles. So the binder in the paper was developed based on this mechanism of the pulleys, which I think is quite good explained here in this figure. So by multiplying pulleys that are attached, like using multiple of them, they can move the rope here and use less force to either then lift something, or in our case, pull something together. So if we translate this to our system, they use this ring slide polyrotexane, showed here in yellow, which is a polymer that is ring form and usually non-covalently threaded over a linear polymer on the sides. And they couple this with the alpha cyclodextrin here, functionalized with hydroxypropylate. And the system is covalently integrated with PAA as the main chain, but the functionality can move freely along the thread compound, which the authors claims then lowers the tension on the polymer network and makes the polymer able to hold everything together and compromise the cracks formed during cycling. And this is example I find someone special, because in this paper they do not actually mention the word self-healing at all. But I wanted to draw your attention to this because I think it's important that we start to think about how we define self-healing and maybe start to question if we really know everything about the mechanisms we have in our systems. So I think it's important that we question the mechanism and if we are certain of it. So in my previous example, they only define the binder as stretchy, not self-healing, meaning that the bonds of the polymer does not break and form during the cycling, only follow the silicon particles during the expansion. And then I'm wondering, do we count this as self-healing as well? I mean, does the system have to include the polymer breaking and forming, or is it enough that we heal the cracks of the particle, for example, then of the silicon, for it to account as self-healing? However, in the other examples I mentioned before, where they mention or claim that it's self-healing, the breaking and forming of the bonds during cycling is not confirmed. So technically, those polymers could also be just also more elastic. And do we still want to count that as self-healing? So here I would like to leave you with more of an open question for you to also think about. Where do we as a community draw a line for self-healing? And does something need to break and form for a mechanism to be accountable as self-healing? Or what would be a good definition? So feel free to share your own thoughts in the comments also about how you would define or think that we should define self-healing in the future. So to summarize, most commonly used for these self-healing binders for silicon anodes are hydrogen bonding through PVA. It's also important to start thinking about the scalability for industry use for these binders, because often it's around 20 weight% used in the electrode, and that is way too much for anything that the industry would be interested of. Also, the mass loading is often below 1 milligram per square centimeter, which is very low. So we need to find a way to also increase the capacity of these electrodes. And as I mentioned, it's tricky to find something to define what can be accounted for as self-healing or not. And we need to keep track what is happening to the bonds through characterization of self-healing and to evaluate them. And if you think that this sounds very interesting and want to talk more about that and so on, one day we'll talk about that more later today about the evaluation of self-healing in these bonds. Lastly, I just want to thank my supervisor, Guillermo Hernandez and Christina Edström, and the funding agencies for my project. And thank you so much to the Battery 2030 Plus for the opportunity to speak today. Thank you.
Thank you very much for both your very good and very high level presentation. So we will have a very good young scientist in the future today, but when you will not be young enough. Okay, so we will have then 2 answers during the following presentation of Marta Mirolo and Wondi Woyumdi. I guess, I hope not pronounced wrongly. But now the session is open for Q&A. We have already one, and then I have many, frankly speaking. So the first question is from Mostafa Mohammadi. He asked, are you interested to use your binder on other silicon structures? Because I'm working on 2D silicon and I'm trying to reduce the volume expansion.
Yes, so I don't know if I can ask a follow-up question. Where is this
Yes,
silicon able to?
As it is on binder, maybe it's more for you, Tamara.
Yeah, I don't know. Is this, Mustafa, where are you wanting to use this silicon? Like, my focus is mainly on batteries. So right now we are focusing on nano-sized silicon in the anodes mainly. But yeah,
Yes,
I mean, if this silicon expansion is an issue, the volume expansion is an issue in other systems, it would be good to share.
If I may just try to translate, if I understood what is under this question, I hope, and then Mostafa, please write eventually others. You were speaking about nanoparticles in the anode of lithium ion, but you know there are also possibility to have different structures of silicon with bigger porosities and so on, where you can also add much higher amount of silicon, but they are really easy breakable. And so, yes, they are synthesizing 2D nanosheets. So if you have 2D nanosheets of silicon, the expansion is different than the one of a particle, of spheric particle somehow. So his question is if you are also considering to use these binders for these 2D nanosheets, like graphene layer of silicon, if I understood properly.
Yes, thank you. Yeah. Right now we have only been focusing on nano-sized silicon for our binder system that is based on borate ester bonds. So that is where we're starting right now.
Okay, thank you. Is there any other question? I can try to ask one for both of the two while you are, okay, no, there's another one here already arriving. How do you expect hydrogen bonding mechanism of self-healing can work in the presence of organic solvent in the electrolyte? What is required to trigger hydrogen bond attractions? I guess this is for both of the two. We can start from Mikkel, so that just to alternate a bit. And then for sure also Tamara can reply.
Yes.
Are you here? Okay, great.
Yeah, I'm here. Yes, so for the hydrogen bonding, I mean, there is no, in my opinion, there is no requirement on the presence of water to react. So you can have the hydrogen bonds functionalized to the polymer matrix, and actually through a bit of synthesis, you can functionalize this. For example, quadruple hydrogen bond UPY units to any polymer chain, or copolymerize them. So I think there should be no problem with organic electrolytes. In my opinion, let's see the first part of the question. Yeah, well, it depends also in the type of self-healing. So for organic, for hydrogen bonds on organic electrolyte, that is mostly what has been done so far in the literature, and there are other more complex chemistries that can be explored in the future, which I think is the most interesting thing to be researched in the following years.
Super. And what about the Tamara opinion?
I think it's a similar answer to what Mikael said. I think it's we have shown improvements with the hydrogen bonding with an organic solvent. So I think it's, as I mentioned before, we also need to put more effort into actually discovering how the bonds are reacting within cycling. But my intuition is that they are working with the organic solvent as well.
Thank you. There's another question from Philippe White. He's asking, are there already experiments with the pyrorotaxanes in batteries? Pyrorotaxanes, sorry, but I'm not the organic polymer.
Oh, but it is hard to pronounce, I think.
Thank you.
Yes, so in this paper I showed they've also...
So, do you know?
Sorry. They used it in a battery, and it shows a more stable capacity than, and also this first capacity drop that we usually see in silicon, that is also lowered with this pyrorotaxanes. So in this paper, they have used it in a battery.
Thank you. And what about Mikael? Do you have
no.
Any thought about?
I think Tamara answered this very well. For my presentation, I didn't include any self-healing with this group, so I'm not really sure for polymer electrolytes.
But we have a question for you now. Thank you for your presentation, Mikael. As for polymer electrolyte, ionic conductivity, mechanical properties trade-off relationship still remains a major bottleneck. Are self-healing polymers electrolyte able to mitigate this issue? What are the motivation of self-healing polymer electrolytes in batteries? Wow.
That's okay. Yeah, that's a good question. So it's true. This mechanical properties and ionic conductivity, this trade-off is still a bottleneck for solid-state batteries with polymer electrolytes. Mainly, most of the works that use polymer electrolytes in the literature use gel polymer electrolytes, so with some kind of a plasticizer trapped in a polymer matrix. And one of the reasons is that while you want to be able to increase ionic conductivity and to reduce the operating temperature, and in self-healing particularly, since when you activate the self-healing mechanism, you in some of the cases you will need to trigger this with the use of a temperature. So gel polymer electrolytes will solve the problem of ionic conductivity, and also will allow you to cycle at the temperature in which you will not have this self-healing functionality. So you will have a slower kinetics, and then you can activate the self-healing functionality through the increase of temperature. And I think in the literature we are seeing more and more this transition from this solid-state polymer electrolytes such as polyethylene oxide to a lower molecular weight polymer with a plasticizer, such as a gel polymer electrolyte, a lower molecular weight polymer.
Thank you. There's another question for Tamara. Thank you both. Thank you for both of you. One question for Tamara. It is a good point that you mentioned about industrial interest, as I'm interested to know the progress of the research in the field, whether it's being commercialized or used anywhere in the production scale as far as you are aware of. Or what are your thoughts on the timeline until self-healing research being applied to industry? We need the magic wand.
Yeah, yeah, that's interesting. To my knowledge, I haven't heard of any examples in industry where they have used this, but also being quite young, maybe one of the seniors has a more indication of the timeline. In my opinion, it's quite far away to be on industrial scale, since we're still using quite high weight percentages of binder in our lab cells. Maybe someone else has another opinion.
Just to complement the answer from Tamara, which I mean, I think she's right, and yesterday, Robert Domingo mentioned on his presentation that that Tesla is looking for self-healing functionalities on binders for silicon anodes. So I think it's a very promising field, and I mean we are a bit far away from commercialization, but I mean research moves very fast. So there are a lot of promising works on this topic.
I fully agree with you. As now there's no open question, but please, we have still time, so we were quite in advance. Commonly we are always late, but today we are not so. I just try to add one question to both of you. Do you think that all these additional aspects related to self-healing and maybe also sensoring, eventually smart functionalities in general are adding complexity to the whole system? So how this can affect, in your opinion, recyclability of batteries? Because we have to always keep in mind that the European batteries are born to be recycled, so at the end of their life. So do you have any opinion about? Please, Tamara, please.
Yeah, if I just start at the end of, I think it's of important to also, because I think we also tend to add compounds to systems to see if it's working better, and not thinking at all if this would be how this compound is synthesized, or if it would be utilized in a process in a good way. So as you say, also, I think it's important to think of the compounds we add to the system to really ensure that a production line would be able to handle a synthesis of these compounds. Because I think there is an issue to making it too complex.
What about your opinion, Mikkel?
Yeah, in my opinion, I mean, batteries are becoming more and more complex, particularly lithium-ion batteries, starting from the concept from Sony back in the 1980s. I mean, we are adding increased amount of additives to the electrolyte, and nowadays liquid electrolytes have a vast amount of additives, and even additives that are present in less than a 0.5 weight percent in the liquid electrolyte. And I mean, when we move to, for example, in the case of what I presented with polymer electrolytes or with polymer binders for silicon, the use of self-healing additives will be might have a similar impact than the use of additives on liquid electrolytes, and of course this will increase the complexity of the battery, but we must have this into account for the recyclability of the battery, and at the end it will probably have to be the battery manufacturers, the ones who give a hint to the companies in charge of recycling on how to recycle these materials. Obviously, not two batteries from different manufacturers will be the same. So this is something to be taken into account. And I mean, projects like battery2030 in the European Union are very important in order to establish some guidelines for this.
And also this way will make the difference between the producers. So they add another value somehow. So as there are no other Q&A, I take the last one. Please.
Yeah, I have a follow-up comment.
Yes, sorry,
not really a question,
I couldn't see you.
No, it's
please.
Okay. But I thought when you are asking about recyclability, and I was at the same time thinking about processability, especially when we are focusing on binders. And for silicon, research has gone really far into doing this with aqueous base, and that's something that I think should be continued even with self-healing. And what I see sometimes in literature is that there are new self-healing functionalities that might not be soluble or dispersible in water, and therefore we take a step back of going to organic solvents instead of continuing moving forward with aqueous-based processing. So I think that's something maybe to keep in mind when we design new functionalities, that we try to fulfill this recyclability as well as sustainability.
Fully agree. That was also
thank you
the
for the
aim
nice presentation. Yeah, thank you.
Very good, both. Just one more, if I may, as there are no additional questions in the Q&A. I was just checking. My last question can be, you both spoke about the anode mainly. What about the cathode? So is, in your opinion, the same kind of self-healing polymers or binders be usable also for cathodes? Then, of course, it will depend on the voltage of the cathode. Why the most of people are concentrating and really taking care more about the anode than of the cathode because of the complexity or whatever? What's your opinion? Let's start from Tamara eventually.
Yes,
if you wish.
Yeah, so my project is based on the anode, but I've been seeing in literature the cathode has different issues and require, of course, then different binders and different solutions. So I know, for example, with sulfur cathodes, I think self-healing would be able to be implemented, but I think it's might be more of a complex system. And I think the focus on the anode is because or in my opinion, quite an easy mechanism to understand and easy to see where the self-healing could make an improvement within the cracking, for example. Do you want to add things, Mikael?
Yeah, thanks. Yeah, so in my opinion, most of the efforts are focused on the anode, since currently is probably the limitation for lithium-ion batteries in terms of energy density. So moving to silicon-based anodes or lithium metal. So I mean, that's why I think most of the research is focused here. However, there is still room for improvement at the positive electrode, possibly related to particle cracking, oxidation of the electrolyte, or corrosion of the aluminum current collector, as I mentioned during the presentation. If to the question that if the same techniques can be applied, I would say that yes, the same techniques can be applied from the anode to the cathode, but probably not the same materials. Thinking on the electrochemical stability window of the materials, it is very difficult to find a material that is stable chemical and electrochemical stably with a negative electrode, and at the same time with the positive electrode. So in my opinion, the techniques would be similar, but possibly the materials would change. I think this is a point that was made yesterday during the Hidden project presentation, and I think it's very important to take into account.
Great, thank you very much. Is there any other question? There's nothing in the Q&A. So even if a little bit earlier, we thank you both very much for your very nice and seminar work. So let's hope to meet soon or also in person, for sure in May in Uppsala for the General Assembly of Battery 2030. So register also for that. So we can take a break. The break ends at 11:20, where we have the two presentations of Wondi and Marta. Marta first and then Wondi at 11:20 on characterization and method to evaluate the self-healing properties.